Yeah, first of all, I'd like to thank the organizing committee for putting this nice workshop together and for the invitation. And well, as you see, my title is a bit pompous. I'm not going to answer to that very question. I'm essentially going to give you my perspective as a quantum dynamicist on quantum computing after discussing with my colleagues, who are most of them in the audience. And well, it's really my naive point of view. And I'm not sure that I'm going to bring anything very new, or that I'm going, and maybe I'm going to ask questions that are unfeasible. Yet, it's still interesting to change slide. Yes, okay, it's working. Yes. Okay, so yeah, well, that was my foreword. And so you can find more technical details by talking with those 4 people who are in the audience and who are going to give presentations tomorrow and the day after. Yet, it's not completely naive because we've written a paper together. So with Bruno and Sad, we investigated the possibility of, well, they investigated the possibility of calculating what we need to do non-adiabatic quantum dynamics. And so after discussing, we sort of make things clearer, and then we applied that method to calculating direct quantum dynamics through an internship, and that's being continued by the postdoc of Martin Beseda here in the audience. So what are the objectives of quantum dynamics as a field? Say, okay, well, a quick summary, a bit hasty, would say, well, it's everything in computational chemistry that is not quantum chemistry and that is not classical molecular dynamics. Because you could be interested in the motion of electronic wave packets, so it's quantum dynamics. And you could be interested in the eigenstates, the vibrational eigenstates, raw vibrational eigenstates, and that's not dynamics, but that's still historically that's the same Hamilton. Well, that's the same Hamiltonian than quantum dynamics, and historically, well, that's the same community essentially. Okay. But typically, when we say quantum dynamics, molecular quantum dynamics, we'll think about the wave packets. Okay, vibrational wave packets or vibronic wave packets. And so, well, the aim is to consider things beyond Born-Oppenheimer or beyond the static description of a molecule at equilibrium. So that could be electronic coherence. So if you consider that you create an electronic wave packet, not only a single state, that could be vibrational tunneling in the ground state. And that could be the role of vibronic non-adiabatic couplings in photo-induced phenomena. Right? Yet, it's not quantum chemistry, but we strongly need quantum chemistry as an input to produce potential energy surfaces. So they work together and we have the same problems. And if there is a benefit of quantum computing for quantum chemistry, that's an indirect benefit for quantum dynamics. Okay, so quickly, well, you probably know, but if we address vibrations in a molecule, it seems very remote from addressing electrons, but in fact, we just are dealing with 2 different Hamiltonians, right? The formalisms of choice are not always the same because it might be easier to treat the electronic problem in second quantization. You're dealing with fermionic indistinguishable particles, but when you treat vibrations, you are essentially considering degrees of freedom that are spatial coordinates, and you will be more at ease with first quantization and local representations of the Hamiltonian. The Hamiltonian is different also in that the potential energy is no longer something that you know in advance. It's not the Coulomb potential with restricted to 2-body terms. It's something that you don't know, that you have to calculate numerically first and possibly fit to a mathematical expression. So that's the hard work in dynamics that you have to do first, or you do it on the fly. Okay, and well, we also use basis sets, so they are not orbitals, but they are similar to orbitals. They are orthogonal polynomials, or we could also use plane waves or such things. Okay, and often in quantum dynamics, we'll have a time-dependent picture. Now, as an outsider, my perception of quantum computing is that it's essentially a machine that is able to do a unitary similarity transformation. You have a state as an input. The machine will create this well, you encode a unitary transformation and you want to measure an observable. So the observable, you can either consider that you measure the observable for, well, lambda being the parameter that you tune, okay? You can measure the observable on the output state, but you could also consider that you have an input state and that and if you use something that looks like an Heisenberg representation, that's actually the machine here. Okay, so you start with this and you end up with that. So where do we encounter similarity transforms in quantum chemistry or quantum dynamics? Well, you know this. First, obviously, when you are interested in an eigen problem, so an eigensolver, you can cast it as a unitary transform, similarity transform, sorry. And you could also be interested, I will come back to this later, in undiagonalizing something that you have solved to produce a representation that for which the Hamiltonian is no longer diagonal, but for which the states have interesting properties, and they will be called diabatic states. Obviously, in dynamics, you could think of the propagation problem, okay, and here either you write it that way or you use an Heisenberg representation. Okay, so yet again, you have an operator, an observable, and you have here the unitary transform, the unitary operator and its inverse, and that's similarity transform. You could extend this to imaginary time to find eigen energies by collapsing a gas and letting it evolve with an imaginary time. Here, okay, I have replaced t by minus it. So you have a relaxation term here. And if you wait for enough, you will end up on the ground state and you can measure the eigenvalue of this ground state. So that's something that we do quite intensively in quantum dynamics. Yeah, to obtain the ground state of a starting point for another propagation. Say, okay, you want to start from the ground state in the electronic state, vibrational ground state in the electronic state, you relax, and then you send it to the excited state to induce photochemistry or a spectrum. Okay, so what is the added value of quantum computing for quantum dynamics? Again, from my point of view of an outsider who does not do it technically, well, if there is a way to produce an eigensolver for quantum chemistry that is able to deal with large active spaces, that's good for me because I will have access to potential energy surfaces with a better accuracy. Right? The problem is more intensive. But then my benefit is that I have better accuracy for the potential. But I could also be interested in solving a vibrational eigen problem. So that would be the same tools, just a different Hamiltonian, a vibrational Hamiltonian. And I could then maybe get to larger ansatz for the vibrational wave function in many dimensions, right? Or with better correlation in it. Naively, when I discovered quantum computing, I thought that, well, the obvious problem was the propagation, because it's a propagator, essentially a propagator. Now we've seen, and we probably see other talks that show that it's a delicate problem and noise is the big issue here. Okay, so you all know this with basic knowledge for quantum computing. Yet, maybe there is hope, and there are two applications, either real-time propagation, if you want to simulate a problem out of equilibrium where you're interested in the time evolution of the system, or to perform from Fourier transform spectrum using linear response theory. Okay? Much as in the quantum phase estimation method. It's propagation and Fourier transform to get a spectrum. We do it in quantum dynamics. And I'll come back to this. Another aspect that is a sort of unexpected thing that seems to be the cherry on top of the cake is that especially SAVQE seems to be prone to produce naturally diabatic states without diabatization. If you stop at the last step of the block diagonalization, it's likely that it's a diabatic representation for free. So it's under investigation. So I decided to put those two slides that are very probably play school, and you know this, but it's just to set things and go beyond. So if I consider a real symmetric Hamiltonian for a two-state level, I can encode the Hamiltonian with expand the Hamiltonian over Pauli matrices. Okay, and I can encode the rotation that diagonalize this Hamiltonian using also Pauli matrices with as a generator of the rotation. I can expand this also in terms of Pauli matrices instead of an exponentiation. Sorry, it's not working. And I can be interested in the time-dependent problem, writing the propagator of the Hamiltonian that way. Okay, here through exponentiation of this, which is another way of writing the time-dependent Schrödinger equation. Again, you can see that you're essentially doing a unitary similarity transform here, doing this. U here being the matrix of the eigenvectors. So you see here that I have replaced this full matrix by the diagonal matrix that is that you obtain after diagonalization. Okay, so in the two-level prototype, there is a formula for this exponential of a 2x2 matrix that way. And this formula involves H, but I know H, it's a function of the Pauli, well, it's an expansion in terms of Pauli matrices. So the propagator can be explicitly written at any time in terms of Pauli matrices. Pauli, well, yeah. So it's exact. It's cool, but it's a two-level problem. I can generalize this to larger spaces, Hilbert spaces, with well, the same techniques as when you produce a circuit. Okay, same algebra. But if I want to express explicitly my propagator, I still have to solve first the eigenproblem. Okay, so I end up with the exponential wall. Maybe this will be held by quantum computing, but yet I have to reconstruct a large matrix. So, okay. So anyway, even not talking about quantum computing, what we do in quantum dynamics beyond the two-level problem, which is exact, if we cannot afford to diagonalize the Hamiltonian first and store all the spectrum and the whole unitary matrix of eigenvectors, we have to do approximations, and the first one is based on simply using time stepping and approximations of exponentials of operators. Approximations that have to be governed by an error that is of the order of a power of a small time step. So the most famous one is the strength splitting, okay, which is based on the Becker-Campbell-Hausdorff formula. There are many ways for this. It's a nested commutator expansion. So if I want to, if T and V, the kinetic energy operator, and the potential energy operator that constitute the Hamiltonian, if they do not commute, like this sort of trotterization has an error of order 1. It's not good enough for dynamics, it's never used. And what is often used is the second order split operator technique, where you have here a 1 and a 2 factors, and you can continue. There are formulas for up to, I've seen one with 16 terms, and actually you are not the best factors that you put when you divide V and T are not integers. And there are real numbers that have been calculated up to 6 decimal places. Might seem stupid, but that's for accuracy, and that's by mathematicians. Okay, so wanted to address a funny problem. What is nice here is that you don't have to diagonalize H, but you have to use diagonal matrices at some point to make it efficient. And what is nice is that V and T are diagonal in the Dirac basis and in the reciprocal Fourier basis. Okay, so essentially, if you play with Fourier transforms and you insert them in between each term where you have only V or T, you can start with a grid representation of your initial state. V is diagonal on the grid, okay, with of values of positions. You Fourier transform, you get something in K space, you know, T in K space of a diagonal matrix, P square over 2M. You back Fourier transform, you get back to a grid representation, and you have this that will act on the grid representation to produce the wave packet at time T plus delta T. And you can even show that this formula is still unitary, symplectic, etc. for time-dependent potentials. Okay, but you have to be careful about the time at which you apply the first half potential and the second half potential, and that looks a bit like the Verlet algorithm in classical mechanics, dynamics. Okay, but still we are limited to small systems with this because we have to deal with large matrices anyhow and large vectors and so on. So in practice, say 6 degrees of freedom is reasonable, which is a 4-atom system if you are considering vibrations. So not big. So there are alternatives to this. So now I'm going to go to variational approaches, but there are alternatives that are still, well, say they are good for longer times. So you've got longer time propagators, but still limited to small systems such as the Chebyshev expansion, right? But I'm not going to talk about it. And it's not a unitary transform. So, okay, so well, the current alternative is to now work on not on the operator, but on the expression of the solution itself, and assume that you have a simplified approximation that is that depends parametrically on parameters that you would optimize in the time-independent problem, and that you will propagate with equations of motion, ordinary differential equations of motion in the time-dependent picture. Okay, so essentially, U here is mathematical function that you impose. It has an expression that depends on the degrees of freedom X and on the parameters lambda explicitly. Okay, so you can define mathematically what is called a manifold. The manifold might be a cursed space or a linear space. It depends on the type of ansatz that you use. Okay. And the crucial point here will be the tangent plane of the manifold at a given time. So at a given time, you assume that you know, say, the time 0, you assume that you know your wave packet. And you have to calculate variations, first order variations of the approximation when you vary the parameters. And that defines a plane that is tangent to the curved manifold. Okay. And so you are going to have to use tensor analysis tools, such things, or say it's the same as when you use a moving frame with curvilinear coordinates. It's the same mathematics. In the time-independent picture, there is also a variational principle. I guess everyone knows it. Here is the Rayleigh-Ritz variational principle, in which you write a functional here of the parameters, that is the Rayleigh quotient. Here explicitly written in a situation where the ansatz may not be normalized. And then if it may not be normalized, you will have to impose a constraint in the form of a Lagrange multiplier, right? But then you assume, okay, you know that your approximate best solution is the smallest of those when you vary lambda, and this smallest script E of lambda 0 optimal is always larger than the exact ground state energy. At optimality, at stationarity, you assume that you have imposed the normalization, and because it's a stationary solution, you know that you are not going to vary to first order, which means that essentially all the derivatives of this functional will be 0, so the gradient in the parameter space is 0. Now the curvature might be negative, but we never check, or we should, and sometimes people do, but typically it's a first order method. Now, I'll go back to the time-dependent variational principle. It's not the Rayleigh-Ritz variational principle that I use. It's the Dirac-Frankel variational principle. You still see here that I'm playing with first-order variations. Here, it's the left-hand side and the right-hand side of the Schrödinger equations that I have put on the same side. So you have here at the time derivative minus the Hamiltonian applied to the ansatz, and overlapping this with first order variations, this should be 0. Geometrically, you can show that it actually means, although it's a bit more complicated, but it essentially means that you have access only to the tangent plane, because the first derivative is a first variation, first order variation. You would like to escape this constrained manifold, but you cannot, so that be the true solution. The difference between the two here is orthogonal. The best case, the smallest distance from the actual solution to the approximate solution has to be the orthogonal to the tangent plane. It's the orthogonal projection, because any first order variation of the solution belongs to the tangent plane. So geometrically, it's very easy to understand. My best approximation over the table from that point is the orthogonal projection. It's the smallest distance. Okay? That's what it means. So there are mathematical precautions to take, whether you consider real or complex parameters and so on, but geometrically, that's the story. And it's nice because it's unitary and it preserves energy thanks to symplecticity. Geometrically, as I said, it's very similar to curvilinear coordinates. Okay, so imagine that the manifold is a sphere. Okay, you are wanting to use spherical coordinates. You have the radial unit vector. You have the tangent one with respect to the latitude, and the tangent one with respect to the longitude, and they move. If you move over the sphere, the moving frame moves with the point. It's exactly the same here, and it's actually easy to show that the unit vector is the derivative of, well, the unit. The basis moving, the moving basis vector is the derivative of u with respect to each lambda alpha, and that's a set, and that's exactly what you would do if you were going to define mathematically u r, u theta, and u phi for spherical coordinates. You differentiate r, vector r, with respect to r, theta, and phi. The parameters, exactly the same in mathematics. So, as I told you, and now if I'm really interested in getting to the equations of motion of the parameters, because that's what I want to solve, not the wave packet on a grid, but the time evolution of it's defining parameters. Well, first I can consider that the variation of the approximation, the time derivative of the approximation belongs to this tangent plane because it's a first order variation. So I can expand it over those basis vectors. And here the coefficients, they are the time derivatives of each parameter. And I have to do this for each parameter. Now, I'm dealing with a basis set of moving vectors that is not necessarily orthonormal. Most of the time it's not. So I have to build a gram matrix, matrix, here G, that appears here if I overlap. And then I end up with that type of nonlinear equation governing the time evolution of lambda b, okay? And you recognize here that we are getting to mean fields because here I could insert another resolution of the identity and get through this something where I will have to evaluate the Hamiltonian, the matrix, considering this basis of derivative of the approximation with respect to the parameters. Yeah, that's actually summarized here. So because I'm dealing with a non-orthonormal basis, parametric basis, the projector so it's a truncated resolution of the identity to the truncated space. So it's a projector. The projector has to be written that way with a double sum and the inverse of the overlap matrix, right? Which allows me to define an effective Hamiltonian that way, PHP, typical of an effective Hamiltonian formula. Then if I assume that my approximation on the manifold belongs to the tangent plane, I'm assuming contact between the manifold and the tangent plane. Okay, that's natural to do. I can say that U is equal to PU. Then the Schrödinger equation effectively coming from the variational principle becomes, well, first Hamiltonian terms, HF effective applied to U becomes PHU or PHPU, that's the same. Then what I get is this, which is a sort of effective Schrödinger time-dependent Schrödinger equation now for the parameters. You see here that the time evolution of the approximate solution, no, well, for the parameters that comes later, but I'm recasting the variational principle in the form of the exact solution of an effective Hamiltonian. So either I say I have an exact Hamiltonian and an approximation in the thanks to the variational principle, or I built the effective Hamiltonian, which is not the true one, but I can obtain its exact solutions because they belong to the space that I can describe, right? The manifold. So then if I continue with what I told you, if I insert again the projector here and there and blah, 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 and if I can afford to inverse this G matrix, then these are the explicit equations of motion for the parameters. But then I may encounter problems when I have ill-defined matrices, singular matrices, because that may not always be invertible. And then, sorry, I said that I would insert something here. And did I? Yes, I did that here. So that's the same story. Now, I'm considering that because the approximation belongs to the tangent plane, it's a linear combination of the basis vectors. I have coefficients, whatever they are, C. I can consider that there are sorts of projections of overlaps of the approximation over the basis, but because it's a non-orthonormal basis, I have to play with reciprocal and dual, covariant and contravariant components. That's just non-orthonormal algebra. It's fine. If that were one, I would have here just the overlap as a coefficient. And finally, I end up with Galerkin type ordinary differential equations of motion for the parameters. So you see that here, those numbers, I obtain them from those numbers thanks to a mean field. And because it's non-orthonormal, I have an inverse Gram matrix here, but that's essentially a mean field. I can do the same in the time-independent picture now. So if I'm addressing, say, a state-specific problem and I want to impose a normalization condition, I will have to introduce one Lagrange multiplier in that way, optimize the Lagrangian or find the stationarity condition, blah, blah, blah. I end up with this. If I'm working with real valued basis functions, essentially, I end up with something that looks very much like the Dirac-Frankel variational principle, except that in the place of the time derivative with IH bar, I have this Lagrange multiplier that smells like an energy. And actually, that at stationarity, that's the energy, the approximate energy of the approximation. So I can use exactly the same techniques I showed you before to have a parallel version of the time-dependent principle in the time-independent world, but using this tangent plane story and effective Hamiltonian rather than working directly on a specific problem. Here I can express a very general solution. I build the effective Hamiltonian to which I'm looking for an exact solution. I have to build a projector at some point, and I end up with a nice Schrödinger equation, but it's not nice at all because it's nonlinear. Because now the effective Hamiltonian depends on the solution, so I have to know the solution. So I could exemplify this to Hartree-Fock, SCF, etc. if I'm dealing with a nonlinear problem. But the general solution of the variational principle could be recast that way with a mean field. If I'm dealing with nonlinearity, I have to build that matrix and invert it. And here I have the coefficients that looks like a nonlinear circular equation. And well, obviously, it's always nice when we can work with a fixed basis set. So I'm no longer considering a moving frame. I'm considering a flat manifold, which identifies everywhere to its tangent plane. Essentially, I'm working with Cartesian coordinates, so to say, because I'm working with a fixed basis set that does not, but that is a given. And I'm only here optimizing the parameters, the linear expansion parameters. Then this basis, well, I will choose it orthonormal. Obviously, it's easier. Okay, no G, I don't care. I can express this first order variation that way with first order variations of the parameters. You see here that those phi alpha, they play the role of my ancient moving vectors. And I end up with, simplifying things, with secular equations here and Galerkin equations. That's the same, but in the time-dependent world. Here you see that I have this matrix of the Hamiltonian represented in the basis. That is a given. I can build it. Then I have to solve an eigen problem, discrete, finite. And here I have to solve the equivalent, but for propagating the parameters. Same story. Okay, so now if we stay in the time-independent world, quickly said, we could say that full CI is an instance of a linear variational principle. So essentially, formally on the paper, I'd like to do a full diagonalization. I may not be interested in all the eigenvalues, though I could do a block diagonalization, but mathematically the problem is this, and I may want to do it for all the states, but I may be interested in one state. Now, if I'm using optimized orbitals somehow in an SCF, Hartree-Fock or Conchamp procedure, or in multi-configurational version of it, I have to deal with orbital optimization. Those are an example of the nonlinear set sorry. Oh. Say here, for instance, the derivative of the approximation with respect to an orbital is, say, for instance, a determinant in which you put a hole, and you are going to calculate mean fields in which you have all the orbitals but one. Okay, and that's exactly what this means in practice. Okay. And then, okay, if you do state-specific MCSCF, you want to do a partial diagonalization, but still you have to deal with linear parameters, CI, and the orbitals that you want to optimize. And if you're doing state average MCSCF, actually you're dealing with an ensemble. So the variational principle tells you that you're actually doing a block diagonalization and optimizing the orbital, blah, blah, blah. But actually, if you write the variational principle for state average, you're not asked to do a partial diagonalization. You're really only asked to do a block diagonalization. The same for SCF, or Hartree-Fock say, you're not asked to produce canonical orbitals. You are asked to produce a set of stable occupied orbitals. Okay. If you diagonalize this, you get the canonical orbitals, but it's up to a unitary transformation anyway. So you're just asked to produce a stable subspace for the Fock operator. In practice, it may be, and that's what we do typically in quantum chemistry with standard methods on classical computers. The easiest way to produce this is to do a diagonalization, maybe a partial diagonalization, but we solve, say, the SCF problem with the diagonalization of the Fock operator matrix iteratively because it's nonlinear, and the same for MCSCF, maybe with an iterative diagonalization, maybe not Jacobi, but it's easier just to diagonalize, at least for some states, but we may do otherwise. Okay, so now, okay, so back to quantum computing. I was talking about state average MCSCF. Okay, well, an equivalent, well, the best analog for it in the quantum computing world is SAOOVQ. Okay, so it's an ensemble. SA, so it's state average. So you're looking for an ensemble of states for which you optimize the orbitals democratically for all of them, and you use a variational quantum eigensolver to mimic a CI problem. It's nice to use UCC because it's QC friendly. You get a unitary operator. Okay, I guess there are other solutions to it, but it's the most convenient one. And if you say you use CCESD, you can map to restricted CAS, for instance. It's a sort of restricted active space for me. It's just a RAS for those who know, but expressed in a unitary way. Okay, to select the configurations. So, okay, you know everything. I'm not going to dwell on that, and you'll see more on it by Sad tomorrow. But that was the method that interested me the most, and I will finish on this later for the diabatization for free. Now, because I'm going to talk about diabatization for free, hopefully, I have to introduce those of you who are not familiar with this. So I have to introduce a bit the adiabatic, non-adiabatic problematic and what are diabatic states. So quickly, here, forget about electrons and nuclei, but say, okay, if you want to have a more concrete picture, you could say that Y is the collection of electronic degrees of freedom, and X is the collection of nuclear degrees of freedom. I separate a Hamiltonian here, a partial Hamiltonian for each value of X, that X being a slow parameter based on physical arguments. So for electrons and nuclei, you will start with the masses, but you have to be careful to show that at the end you are dealing with time scales and energy scales. So it's just a starting point, and that's not always the problem. Say you want to separate vibrations, the masses are not the critical argument, it's more the frequencies. No, okay, so you have isolated for each slow parameter an Hamiltonian that you can consider in the adiabatic picture. So you vary it adiabatically with respect to X if you want, okay, or not. Then you can write your full Hamiltonian that way, kinetic energy operator plus that limited Hamiltonian to the subsystem. you solve it, I can solve it. Okay, so if you're dealing with the electronic problem, at each geometry positions of the nuclei, you solve, you get the eigenstates and electronic energies of the electronic Hamiltonian. You call them adiabatic states. In principle, on the paper for what is going to come next, I will assume that it's a complete and orthonormal basis. Well, orthonormal is fine, but complete never in practice, but I will do so. I will use a ket notation for y because I no longer need y explicitly, but I need x because I need to solve the problem at each x. So I cannot go to second quantization for x at that time. I still have to have a grid representation. Okay. If you do, okay, maybe I'll skip this, but it's just to give you a flavor. I'll go fast, say, okay. So say it's to make a connection with perturbation theory. You solve your electronic problem, I will say, okay, at a given geometry, you know how to vary your electronic Hamiltonian from this given geometry to your next. This is just a Taylor expansion. I can use the wordings of perturbation theory. That's the same, so zero order and perturbation. Then I can do the same for the states. I have variations of the states. I can overlap those variations over the basis, the zero order basis. I get coefficients. Those coefficients, they are going to be very critical for non-adiabatic quantum dynamics when you're addressing photo-induced problems with, say, conical intersections for those you know. But they are never more than the first order variation of the states as they change with the nuclear geometry. Okay, so I'm not invoking any dynamics here. I'm not invoking photochemistry. It's just perturbation theory. Okay, this is the first order variation of the states. I can use that to write the Hellman-Feynman theorem formulas that were alluded in the previous talk. If I'm dealing with exact eigenstates, I can show easily. If I'm not, it's more complicated. That if I know the exact eigenstates, the first order variation in perturbation or the derivative in, well, just derivative theory is, well, to get it, I only need to differentiate the operator. The states, I only need the zero order states. Okay, so for gradient, that's fine. If I'm dealing with approximate states, I have to use Poulet forces. Also, there is sometimes a confusion. Here I'm using the first quantization operator. Okay, but sometimes it's hidden here that it's the expression of the Hamiltonian in the basis. So there are sometimes confusions on where the terms come, but it's all consistent in the literature. But I can also, okay, I can also go to the off-diagonal terms, and essentially I can get explicit expressions for those relaxation terms that I call first order non-adiabatic couplings, but they're not couplings yet. They're just variations. And here you have the off-diagonal element of that derivative of the Hamiltonian, okay, between S and P, divided by the difference of the energies, provided I know them. It's exactly a first order perturbation theory formula for those coefficients, okay? It's the same. I'm just using derivatives instead of perturbations. Okay, so I will go back now to quantum dynamics. So if I do the Born-Oppenheimer approximation, I'm considering that kind of ansatz. One electronic solution and the coefficient in front that plays the role of a nuclear wave packet. There are alternatives to this, but that's the, well, no, well, not really, actually, that's Born-Oppenheimer on a single state. It's good for chemistry in the ground state most of the time. To go beyond, I have two possibilities. Either I use a sum of such states, okay? So I expand over a complete or expected to be complete numerically basis of phi s, you know, sum over s, or I make the electronic wave function depend on time. So it's no longer the solution of a time-independent Schrödinger equation. It's the solution of a nonlinear equation. It's complicated. Federica Agostini has well, I'd like to be here, but whatever. She's the specialist in France. Okay, so I'm not going to dwell on this. But what I want to say is that if I say, okay, forget about the exact factorization with the time dependence, but I have similar equations. So rather than sums, I have non-adiabatic couplings that depend on time in the form of a potential vector. Here, if I'm using a sum of states, I get coupled equations. It's easy, actually. It looks complicated, but okay, I'm assuming that expression is a sum of products of functions that both depend on x. If I want to apply the Laplacian in the kinetic energy operator of the nuclei to make them move for dynamics, I will have to differentiate products. Okay, so I get three terms. I differentiate on the left, twice the bra, twice the cat. Say no, it's not a bra and a cat, but that's well, okay, the product. So the left twice, not the right. Once times 2 plus I don't differentiate u and I differentiate v twice. Okay. So I get three types of terms if I overlap here because I have okay, that's a Kronecker. The Born-Oppenheimer-Hamiltonian acting on one wave packet and terms that come from the fact that the electronic states depend on x parametrically. So first order here and second order. So those are the non-adiabatic couplings. They are not nice because remember that they diverge if I have degenerate solutions. So that will be what we call a conical intersection. So if I'm not lucky, or if I'm lucky because I'm interested in that property that I have a degeneracy, then those couplings, they are horrible and they are ill-defined, in fact. So I don't want to deal with them. I want to change the basis in dynamics with a unitary transform to get to what are called diabatic states. Okay, so that's another basis. So the representation of the electronic Hamiltonian is no longer diagonal. Say here, those are the eigenvalues of the electronic problem. I'm transforming to another basis, so I have to deal with the full matrix, but I want this basis to get rid of the coupling. So sorry, I'm going to skip this, but it's not, well, it's just differentiating products again. What I want is that the new couplings become as much as possible close to 0. Okay. So A are the couplings that may diverge in the adiabatic basis that you calculate. You want to find a transformation U that is such that the new couplings, so say the new relaxation factors, okay, the overlap of a wave function with the derivative of a wave function, become small, almost 0 and negligible in practice. I end up from this to that. Okay, so I have a differential equation acting on a matrix in many dimensions. That's a gradient. Okay, acting on a matrix unknown. I want to build it, knowing couplings that may diverge. So mathematically, that's very ill-defined. There are solutions to it. Okay, we have applied it in several instances, but it's not a nice problem. Okay, so we've applied it, for instance, using data coming from SA00VQE interface with quantics to produce energies, couplings, gradients, to propagate wave packets. Okay, I'm not going to enter the details, but we did this. We interfaced thanks to the work of Julia Attar and continued by Martin Beceda and supervised also by Bruno Sanjean. We have tested an interface using a simulator of quantum computing to produce data that are useful to run quantum dynamics. Okay, and there is a hidden diabatization. It works. Even if it's, I told you it's complicated to get this U, it works. Okay, now I'm going to finish with this. Something that we were very interested with Bruno and Sad was that actually when you think about the SA-VQE method, which is essentially you're formally you are asking the algorithm to produce a block diagonalization, no more. So you have explicitly to implement a final rotation from that block to those two eigenvalues that you're targeting. But it's not variational, it's what you do. But when you write an MCSCF SA MCSCF program, you actually do the diagonalization in one go. So, or any SACI problem, say SA, SSCF would be probably better. You do that directly. Here we stop here, and then we add a final rotation. And we said, okay, what are those states and what do they produce as potential energy surfaces and couplings? What are their look? So on that example, that's a toy model, the formaldehyd molecule. We got such curves. So in black, that's the average of the energies. It's preserved, okay, the trace is preserved. Here, you've got full lines, you've got the adiabatic energies. So the eigenvalues that you would be interested in if you're only interested in quantum chemistry. But if you do not do this final rotation, you end up with those dashed lines, okay, that really look like diabatic potential. So I didn't put every investigation that we've been making so far, but we've done other cuts, okay, it looks very nice, but we know that there is an issue which we have not solved yet in SAOOVQE. It also, as MCSCF, suffers from a gauge freedom. Okay? Even in Hartree-Fock, you have this. Remember, I told you, you don't have to produce canonical orbitals to produce a Hartree-Fock determinant. You could use natural orbitals. It's the same, it's up to within a unitary transform. In MCSCF, the unitary transform on the orbital may be compensated by the CI coefficients. If we are interested in producing smooth diabatic states, actually, it's easy to show that you have to work on the CI coefficients, okay, and minimize as much as possible changes due to changes in the orbitals when you change the geometry. So essentially, what we have to implement is diabatization of the orbitals in the spirit of what is in MORPRO. So there is this paper by Werner and collaborators, okay, when they show the concept, and that a practical ab initio diabatization scheme that was actually, I'm stopping them, that is an old story, would be best achieved if we could diabatize the orbitals, make them change as little as possible with geometry, and and force the CI coefficients to do the same. And with SAOOVQE, they do it for free. Okay, yeah, because we block diagonalized, and we are. I suspect that the machine is not going to be doing effort for no reason. It's lazy. So it's going to find the fastest route to do block diagonalization. So I suspect it's a sort of case where what is formalized by Sederborn and co-worker is a way to say, okay, the unitary transform is the closest possible to unity. It's the laziest one, okay? And you can show mathematically that you would achieve it that way. Then I'm going to stop. Thank you for your attention.
Okay, thank you very much. Questions from the audience? Yes.
So I think maybe I didn't get the last point because it was a bit fast, but so you did VQE for 3 excited states and you found always diabatic curves. That was the gist.
Yeah, only the black line is the average. It's just the ensemble energy. So it's red and blue. So the ground state and the first excited state.
Yeah.
The ansatz actually mimics a CAS4-3. It's an pi n pi star problem essentially with an n pi star transition. And so we focused on the ground state and the first excited state. And then when you do this, you get, well, if you do the total job, you get the adiabatic energies. Okay, you get an avoided crossing here. If you stop before, so you stop at the block diagonal step.
Then you get to diabats. That's what we the dashed lines. Then.
The dashed line. No, okay. So well, when you diabatize, you know this, and you want to produce the dashed lines and also the coupling. Okay, it's not plotted here. So it's complicated, it's nasty because you have to use the non-adiabatic coupling as much as possible, which is ill-defined. Now, VQE, SA VQE, does this first. And then once you know this, well, you add a final rotation that is beyond the variational principle. It's just convenient. Well, that's because you are not only interested in minimizing the trace, you want at the end the states and their energies. So with VQE, we get, say, the green and the orange here. They are the dashed lines here. Okay. And usually we don't have access to them ab initio.
Thanks, Benjamin. That was very interesting. About this point, did you check if the non-adiabatic coupling was small on your dash line around the avoid crossing or whatever?
The one that we would get ab initio.
Yeah, sure.
Bruno, do you remember if MEL,
because that would be very interesting
in the diabatic or in the basis before the final rotation? I'm not sure, but now we are doing it the other way. We are checking the angle because it's a 2x2, so we get the angle, or we could extract it, differentiating the angle, checking with the coupling, but there is the CI and the CSF contribution. So that's why at this stage it's not it's still under investigation, because the CSF contribution, say from the eye, the CSF contribution is small around the crossing, so it's fine. The CI contribution dominates, but we didn't apply any constraint. Then we wanted to investigate more globally, and when the CSF, so the orbital contribution to the coupling, becomes larger than the CI contribution, it's not, it's not well defined. So yes, well, that's something to do. And numerically, I don't remember if you did calculate the couplings. So we could actually, yes, I guess it's for free. So.
And I guess around this point, there is a conical intersection.
Yeah.
And did you try to reach this point?
Oh, yes. Well, I'll show you if you want later, but yes, we have several cuts with different values of the dihedral angle along this bending angle. The conical intersection, actually, it's when you keep CS symmetry. You go through it, you get the diagonal elements that follow nicely the adiabatic, but not swapping.
Okay.
Naturally. Okay.
It means that your dash, let's say dash surface, are very smooth.
Yep.
Okay. With the coupling as well, which is smooth.
Yes.
Yeah, that's good.
So it's difficult in regions where the CSF contributions become larger. Then we have to work on the orbitals. But when it's naturally the case, then yes, they are super smooth. The angle is super nice. The coupling goes that way.
But in this case, even if the orbital contribution part is not so small, it doesn't really matter. I mean, what's matter is that the curve are smooth.
Yeah.
Okay.
But when they are not, then the CI contributions is not so dominant, so it becomes more erratic.
Okay.
And then the curves are not so smooth, as if you were missing this driving force of the CI coefficient, so to say.
Okay, thanks.
Thank you for the next. If you go back, there, like, do you now know the unitary that does this? Like, you have a prescription for the.
Yes.
So, are you still searching for this unitary, or?
The problem is that mathematically, you can show that this is a sort of loved in, okay, and that's actually people who've been using Procrustes analysis such. Wow, you can show after many pages of math that in fact that's the simplest solution to be the smallest transformation. The problem that is hidden here is that you have to consider overlaps between different points. Do you have to propagate? You have to have a fixed reference. is the problem going to be path dependent or not? That's the whole problem. And fixing the science, the relative science, that's also a nightmare. So
So here then the overlap goes to 0 or becomes 0.
yeah,
or-
that's also horrible. So,
Yeah.
yeah. So it looks simple, and as I told you, that dates back from the late 80s. But those people have never used that method in practice except for very small systems, because it becomes untractable as such. And so what we want to do is to avoid that. We want to avoid to integrate the differential equation acting on U, the previous one, but we don't even want to do that because it's not so easy to define and propagate. We want to have this for free, thanks to VQE, and then work on the orbitals.
Okay, you would need to propagate S, and that's as costly as propagating U, and then you don't gain anything.
And then you may end up with path dependence. And
Okay.
that's not practical.
Okay, thanks. Any more questions? Maybe from the Zoom audience? If not, let's thank Benjamin for the nice talk. And we see you at lunch.